Hey, I hope you're doing well today. I'd like to spend a few minutes talking about problems, still counting problems, that use not in the directions or in the directions, and how you handle these is different. But I would like to reflect back on some information that you already know. You know, we've talked about set theory in this class, we've talked about logic in this class, and you already have information about arithmetic before you ever took this class. But remember we talked about a complement? And a complement are all the values that are in the universal set, but not in the set you're taking the complement of. Whereas in logic, we say the word not, which means everything but that, right? And then arithmetic, what corresponds to that is subtraction. You say A minus B, that means everything in A, not in B, right? You just subtract out B. And we also talked about in the red here, the connective of a union. And really, union means or. When you talk about combining sets together, if you put them together, then the value could be in this set or that set, and that's a union of sets. Whereas or, we use that in logic, means this thing or that thing, or both. And or means plus as far as arithmetic goes. So we want to apply that same idea to counting problems. So the complement, we're going to start with the complement, then we'll do or later, but the complement's principle of counting. So the number of ways in which a certain condition can be satisfied is the total number of ways, the total number of possible results minus the number of ways the condition would not be satisfied. It's actually a little easier than this reads. Symbolically, if A is any set within the universal set U, then the following formula holds. So basically, you have the number in A, that's how many things are in set A, is equal to the number in set U. Now remember the set U is everything that you're talking about for that particular problem, minus the number in the set A complement. And again, then when you see that in action, I think you'll feel a little bit more comfortable with this definition. So we want to start off with a problem right off the bat. So example A, find the number of proper subsets of the set S, and the set S includes A, B, C, D, E, F, and G. Now you'll have to remember from the sets topic that we talked about, proper subsets are all the subsets of your set, not including the whole set. So the subset A, B, C, D, E, F, G, in other words, every single element that's in the set is a subset, but it's not included in the list of proper subsets. So proper subsets are always smaller than the original subset set, right? Now, we could list all the subsets of A, B, C, D, E, F, G, but you notice it didn't ask us to. It asked us to find out how many. Now, we learned from the set section to find out how many subsets, the number of subsets is always equal to 2 to how many elements you have. So notice we have 1, 2, 3, 4, 5, 6, 7 elements. So the number of sets, or subsets, is 2 to the 7th power. And we know 2 to the 7th power is 128. Okay? So there are 128 subsets of the set S, which includes A, B, C, D, E, F, and G. And you know, you could start to write them down, but that's a bunch of subsets. So you have the set A by itself, the set B by itself, C by itself, each of them by themselves. The empty set is also a proper subset, and then you could combine A and B together, A and C, A and D, A and E, and every way you could combine 2 together, and then 3 together, and then 4 together. See what I mean? It would get big. But now this doesn't answer the question. What we're going to do is use the complement. Now, 128 is all the subsets. That's all of them. But it asks for proper subsets. So you know what we're going to do? We're going to subtract out the one proper subset, which is the whole subset. The whole set. And it's 128 minus 1, which is 127 proper subsets. Again, it did not ask us to list them. It just wanted to know how many we have. And that uses the complement idea. The fact that we know how many subsets you have completely, and we subtract out the one we don't want to find out how many we have. All right, next problem. If 5 fair coins are tossed, and how many ways can at least one head be obtained? Now, it turns out that this at least or at most idea comes up frequently when you want to talk about the complement. Because, let's discuss what's going on here. So first of all, how many outcomes are we going to have? If we're talking about tossing a fair coin, how many possible outcomes are there? So if we go back to our multiplication principle, you know, you're thinking about the first coin, the second coin, the third coin, the fourth coin, the fifth coin. How many answers do we have for the first coin, or how many possibilities? Are there 2? How many possibilities for the second coin toss? Where am I getting this 2 from? What can land our heads or tails? So 2 for the third toss, 2 for the fourth toss, 2 for the fifth toss. Turns out anytime you toss a fair coin a number of times, it's going to be 2 to how many times you toss it. So if you haven't figured that out already from previous sections, it's 2 to the number of times that you toss it. So in this case, it's 32 possibilities. Now we could list them all. For example, one of the possibilities is heads, 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 right? And heads, 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 tails, and heads, 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 tails, tails. You see what I mean? Every single possible way you could write heads and tails combined together 5 times. That's all the possibilities. And there's 32 of them. Now, they're asking for how many possibilities is at least one head. So you're talking about, you know, of course, the one I gave you, the heads all the way, 4 heads, 3 heads, 2 heads, 1 head, all of those options. Now, it would be easiest for us, instead of finding out how many possibilities is all 5 heads, which is just 1, or 4 heads, which is going to be 5 different possibilities, or 3 heads, which is, I don't know how many possibilities that, I'd have to calculate it. What we could do is find out the complement. So if we say 32 minus the complement of at least one head being obtained. So I'm going to 32 minus the number of at least one head. And remember, this is the complement, so I use that little symbol. Remember, not that. Now, y'all, what is not at least one head? So remember, we're trying to take the complement of this. So this would be 32 minus the number of. Now, what is not at least one head would be 0 heads. Am I right? So at least one head means 1 head, 2 head, 3 head, 4 head, 5 heads. So not that would be definitely would be 0 heads. Now how many of those 32 outcomes have 0 heads? Just the one, right? Tails, 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 tails. 1, 2, 3, 4, 5. I wrote it 5 times. So this is the one outcome where we have 0 heads. So that's going to be 32 minus that one outcome, which is 31 outcomes. Kind of seeing how this works? So instead of finding out how many possibilities had 1 head exactly, 2 heads exactly, 3 heads exactly, 4 heads exactly, and finally 5 heads exactly, and adding all those possibilities together, it's easiest to instead find out how many possibilities you have total and subtract out not at least one head. And not at least one head is 0 heads. And that only happens one way, all T's. And so that's how we got the 31. Okay, so for problem C, if you roll 2 fair dice, say a red and a green, and how many ways can you obtain each result? So really this is 2 separate questions. A sum of at least 3 and a different number on each die. How could we do that? Now, I think it might help to have a list of all of our outcomes. There it is. Remember, we did this in a previous section. Now, you could There's two ways you could do this, especially with all the outcomes sitting right in front of you. You could focus on a sum of at least 3, right? So that's at least 3, that's at least 3, that's at least 3. Remember we talked about the diagonals having a sum, like every one of those that I just highlighted for 1, 3, 2, 2, 3, 1, 4, they all add to 5. And these other ones add to 6. And then all of these, for the longest diagonal, add to 7. And then all those add to 8, all those add to 9, all those add to 10, all those add to 11, and then that last one adds to 12. So the sum of at least 3 of all the ones that I have highlighted. Now remember what section we're in. They want us to use a complement. At least that would be easier, wouldn't it? So let me get rid of all this highlighting I have going on here, just a second. And you be thinking about how we could possibly use the complement to do this problem. Now, first of all, we need the number of outcomes total. Okay, so let's write that down. So the number of total outcomes, because you need to do that to ever use a complement, minus the number of not at least 3. Okay? Now, the number of total outcomes we know is how many? 36, right? It got 6 rows and 6 columns. So 36 possible outcomes when you roll 2 die, or a pair of dice, okay? Minus the number of not at least 3 means less than 3. So, y'all, which one gives me a total less than 3? Not many of them, right? Just that one. How many outcomes is that? Just the one outcome. So this would be 36 minus 1. I'm giving you the impression that the complement is always 1. We're always subtracting 1, but we're not really. Okay? This is just these first 3 problems that we've done. Maybe, just maybe, we can get a different complement on this next problem. So let me erase what we have highlighted here. And maybe we'll select a different color to highlight and try this problem. So it says a different number on each die. Now you could go through all of these, of course, and count which outcomes have a different number on each die. So the 1, 1 is not a different number, right? 1, 2, those are different numbers. 2, 1, those are different numbers. Right over here, 2, 6, those are different numbers. You see what I mean? That's what they mean. How many of them have a different number? Feel free to count them. But it might be easier to use this complement thing again, right? If we have the number of outcomes, this is total, minus the number of the same number, right? If we know how many we have total, and then we do the complement of a different number on each side. Well, what's the complement of a different number? The same number on each die, right? And so the number of outcomes is still 36. The number of outcomes for rolling a red and a green die, or whatever, 2 separate die, or a pair of dice, is always 36. Unless you got some weird die, okay? Always 36. And then you're going to minus, if you're doing a complement, whatever you don't want to count. And how many do I not want to count? Let's go back to my pink. I don't want to count that one, that one, that one, that one, that one, and that one. Why not? Because it's the same number on both die. So how many outcomes is that? That's 6. And 36 subtract 6 is 30. So what is the point here? Sometimes it's easier to just subtract out the ones you don't want to count rather than counting the ones you do need to count. I hope that makes a little bit of sense to you. So let's try another problem. Okay, so if you draw a single card from a standard 52 card deck, and how many ways can you obtain a non-face card? Now I'm going to pull up a picture of cards for you in just a minute, but for those of you who have a good understanding of cards, you know what face cards are, right? Okay, so face cards are a jack. My pen is not working. Stand by. So a jack is a face card, a queen is a face card, and a king is a face card. Those are your face cards. right? So if we want to talk about non-face cards, there are more of those. Those are all the number cards, and your ace is also a non-face card. Okay, now let's look at the cards for those of you that are a little more or a little less familiar with cards. Okay, and notice what it's asking. How many ways can you obtain a non-face card? But look at there, I listed the face cards. So I probably should have listed instead a non-face card. So a non-face card, let's back up, would be, you know, an ace, a 2, a 3, a 4, a 5, a 6, a 7, a 8, a 9, and a 10. All of those are non-face cards. And then you've got 4 for every suit. So it might be easier to take the number of cards and subtract out the number of face cards. Now, when we did our review of cards, we talked about the number of face cards. Let me show you that real quick. So there's your cards right there, right? And we decided that face cards are these guys right here, the jack, the queen, the king. The pictures that I've given you still don't give you an idea of what face cards are because they don't have the faces on there. But a normal deck of cards often has faces to go with the jack, the queen, and the king. And notice how many of those there are. There are 12 of them. So if I rewrite what I had going on, remember we have 52 cards, and we want to subtract out the number of face cards. So I have 52 minus 12, which is going to be 40. Now the other way to do this is just to count the non-face cards. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You see what I'm saying? So there's always a couple ways you can handle this. But now don't throw this complement thing out thinking I don't need it. Because there are some times where you just cannot count the number. You will have to do the complement to get the job done. So make sure you're following what I'm saying here. Now here's a fun problem. F. How many 2-digit counting numbers meet the requirement that it's not a multiple of 20? Now, this one is a dead giveaway. Not a multiple of 20. So, first of all, examples of 2-digit numbers. You know, an example of a 2-digit number is 35 or 47 or 100. Oh, no. 2-digit numbers. Miss Wilson, pay attention, right? 80. 2-digit numbers. All those are 2-digit numbers. 35 and 47 are not multiples of 20, right? They would count in our list. 80 is a multiple of 20, so we don't want to count it. Now, it would be easier to count the multiples of 20 and subtract that from the number of 2-digit counting numbers. So that's what we're going to do. So we're going to figure out, first of all, the number of 2-digit counting numbers. I'm just going to put 2-digit numbers minus the number of multiples of 20. So much easier than trying to count everything that's not a multiple of 20. Now, how do you find out how many 2-digit counting numbers there are? Well, to figure out 2-digit counting numbers, we've done it before, but let's do it again. You have 2 tasks. You need to figure out the first digit, and you figure out the second digit. Now, the first digit can't be 0, right? Because we're talking counting numbers. That's why they specify counting numbers and not just random 2-digit numbers. But counting numbers can't start with 0. So we're talking 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the only possibilities. That is 9 numbers I can put there. But now the second number can be 0. So 0 all the way through 9. Well, that's an option of 10 numbers. This problem didn't say anything about you can't reuse numbers. So I don't have to throw one out for already picking it. So there are 90 2-digit numbers. There's 90 of them. Now, you know what? Multiples of 20 are not that hard to figure out. So y'all tell me, what are multiples of 20? And I'm going to pretend like I hear you, right? So 20 is a multiple of 20. 40 is a multiple of 20. 60 is a multiple of 20. 80 is a multiple of 20. So is 100, but it's not a 2-digit number, right? These are the only multiples of 20. How many of those are there? Looks like 4 to me, so we're going to subtract out 4. And that gives me the answer to this problem, which is, boom, 86. Ready to try another problem? Let's do it. Okay, and here's a fun problem. Carol and 3 friends are boarding an airliner. So we got 4 people, right? Carol and 3 friends. So let's make sure we're comfortable with that. This is 4 people. They're boarding an airliner. There are only 10 seats left. 3 of these seats are aisle seats. How many ways can the 4 friends arrange themselves in available seats so at least one of them sits on the aisle? Again, I warned you about this at least thing. At least one of them sits on the aisle means, if we write that down, that means one of them sits on the aisle. Let me write this differently. So 1's on the aisle, or 2 is on the aisle, or 3 is on the aisle, or, nope, all 4 of them can't be on the aisle, right? Because there's only 3 available that are on the aisle. So we could calculate all that. Or, you know what we could do? We could find out how many possible ways they could seat themselves. Okay, so the number of seating options total, number of seating options total, and then subtract out at least one of them sits on the aisle. What's the complement of that? None of them sit on the aisle. The number of options where none are aisle seats. Again, if you ever see that at least thing, think about the complement of that and see if that would be easier to calculate. Because what I had written down earlier, at least one of them sits on the aisle, you would have to calculate how many of the options have one of them sitting on the aisle, plus how many options have 2 of them sitting on the aisle, plus how many options have 3 of them sitting on the aisle. So first of all, let's just figure out the seating options, right? Okay, now the seating options. Now, you could do your blanks. You got to sit down 4 people. But there's a couple of things happening here. We are not reusing seats, right? So if you're not reusing, remember, you can do a permutation or a combination. The only time you can't do a permutation or a combination is if you reuse numbers, like when you build 3-digit numbers or 4-digit numbers or 2-digit numbers like we did a minute ago, without reuse. So if you're not reusing seats, you can use a permutation or a combination. Now, which is it? Are we talking about a permutation where the order the outcomes are in matters? Or are we talking about a combination where we're just picking a group of people? Well, y'all, if you're picking seats in an airplane, the order matters, right? Because if Carol sits up front, and then friend number 2 sits on row 2, and friend number 3 sits on row 3, and friend number 4 sits on row 4, that is a different outcome than Carol sitting on row 4 and the other one's arranged. You follow what I'm saying? So we're talking about a permutation here. So this is a permutation. Now, what are we choosing? Well, we're choosing 4 seats, so the 4 goes over here. What are we choosing those 4 seats from? The 10 seats that are available. So the number of seating options is a permutation 10 choose 4. We're going to calculate that in a minute. Or you want to? Let's do it now, okay? 10 choose 4, remember, in the numerator is 10 factorial divided by, permutation, you don't divide by the 4 factorial. You just automatically subtract 10 minus 4 factorial, which gives you 10 factorial in the numerator divided by 6 factorial in the denominator, which is actually 10 times 9 times 8 times 7, right? Because you write down the top one to match the lower one, you cancel the 6 factorials. Let's go ahead and multiply that out. So 10 times 9 times 8 times 7, that gives me 5,040. All right, now in a different color, I'm going to work on this other side over here. So the of options that no aisle is selected. Okay, and we got to think about this one for a minute. So first of all, it's going to be a permutation, and we need a permutation because order matters. Again, you're picking seats, so order does matter for a not aisle seat, right? Now, how many not aisle seats are available? So we know we've got a permutation. How many not aisle seats are available? Remember, 10 seats total. 3 of them are aisle seats. How about 7? There are 7 aisle seats available. And how many people are picking them? 4. We don't want this option at all. Somebody needs to sit on an aisle seat. So that's why we're subtracting it out. So this is, again, the calculation of how many possibilities are available where everybody is not sitting in an aisle seat. Okay, so that's going to be 7 factorial divided by 7 minus 4 factorial, which is 7 factorial over 3 factorial, which, now remember what you do. You write down 7 times 6 times 5 times 4. The 3 factorials will cancel, and I'll type that in my calculator. 7 times 6 times 5 times 4. And that gives me 840. And those are the seating options we do not want, so we're going to subtract that out. So my final answer, let's make it in bold red here, is 5,040 minus 840, and that's going to give me 4,000, believe it or not, 4,200 seating options for Carol and her 3 friends. With just 10 seats, but they can rearrange themselves in all sorts of ways. I'm going to wrap this video up here because when I come back for part 2, I want to talk about the OR principle. This first video was all the NOT principle and finding the complement and subtracting those values out. We'll come back and do the OR principle, and then we'll combine some of these problems together. Hope you have a good one.